Thank you for joining today's webinar entitled P2030.10 Standard for DC Microgrids for Rural and Remote Electricity Access Applications, presented by Brian T. Patterson, President of Emerge Alliance. My name is Cole and I will be your event specialist today. All lines are currently on mute to prevent any background noise, and please note that today's conference is being recorded. We will have a question and answer session at the end of today's presentation, moderated by Angie Reisky-Parachis. To submit a text question, locate the question and answer panel on the bottom right-hand side of your screen. Type in your question, select all panelists, and click send to get your question in the queue. Finally, if you experience any technical difficulties during today's event, you may submit a chat to the host. At this time, I would like to turn the program over to Mr. Patterson. Sir, the floor is yours.
Thank you very much, Cole, and thank you, Angelique. Welcome, everybody, to this discussion about a new program at the IEEE P2030.10. And as we start here, what I'd like to do is sort of put this discussion in the context of what's going on with electricity and power systems, particularly in grids and such. We know that there have been many challenges raised over the last almost a decade now concerning the use of electricity, not to mention the increasing use of it with all the new things that we have, as well as the ever-growing population of the world. The fact that we have, in many cases, what's characterized as an over-dependency on fossil fuel, which has ever-limiting resources available to us as inhabitants of this earth, but also some of the consequences of using those fuels in the way we do. We have the growing problem of resiliency in systems as we become more and more dependent upon electricity as sort of a currency of modern civilized existence. We become ever so more dependent upon it, and whether we're worried about weather or other out-of-space kind of things like EMP and terrorist activities and so on, there's lots of vulnerabilities in the way we've handled electricity in the past. We're trying to minimize and mitigate some of those. We'd also like to try to mitigate some of the intrusive nature of an ever-expanding infrastructure. So we're finding new ways to make that more compatible with us environmentally and socially. But the one that hasn't been discussed as much in this context of smart grids and such are the folks who have no grid. This large and growing underserved population, which is estimated to be today somewhere between 1.2 and 1.5 billion people who have no access to electricity directly, and there's probably about an equal number of people who have a limited access or an intermittent access or somehow intrusively not available at times access to electricity. So that's kind of this, it really kind of delves into the whole humanitarian challenge about energy in the democratization, if you will, of energy and making it available to folks around the world who want to become in the mainstream of the economic and progress of the developed world. We have some history with regard to that, and here in the United States in particular, it goes back to about 1916, 1917, when the very first remote microgrids were deployed in the United States in rural America. And I apologize to those who joined us from around the world, and I'm going to focus a little bit on North America, but it's what I know most about it historically, so I'll use that as an example. But at that time, in the turn of the century, about 55% of the U.S. population had no access to electricity. They essentially lived in rural parts of the United States and therefore weren't anywhere near a grid which evolved out of the cities. A gentleman by the name of Charles Kettering, some of you may know the name Kettering from the Sloan Kettering Cancer Research Foundation. He became a philanthropist later on in his life as he made a lot of money in this area of power and power systems. But he invented the electric start motor, which allowed the combustion engine then to be used in these remote microgrids as a way of generating electricity. But because you were typically a single farm and didn't need electricity all the time, Not that the generator couldn't be running 24 hours a day, but you just didn't need it. So it became an intermittent, if you will, a willingly intermittent source. So actually batteries were used to sort of smooth out the on-off nature of the generation capability. In addition, loads became ever increasing because of the invention of the incandescent light bulb, and later on motors and fans and irons and washing machines and refrigerators. Charles Kettering was also the inventor of the modern mechanical or compressed gas refrigerator. So as loads increased, those people who weren't connected to grid needed a source of power, and that's what happened in the United States. Over time, those microgrids served the rural America for about 50 years. The one unfortunate thing is they never got interconnected into grids or even community grids. First, because they were still quite apart from each other, so there were distance issues. And still at that time, the version of the transformer for DC was not invented, something that Tesla did, which really propelled AC into its dominance over the last 100 years or so. But be that as it may, as grids reached these areas, unfortunately, most of these microgrids were essentially abandoned over time as the national grid reached these places, and that was unfortunate. I don't think that we need to repeat that part of the history in what we do going forward for people who have no grid today. So what our vision today is that those roughly 3 million people who have either no or inadequate access to energy, and we'd like to believe that we can give them clean, affordable energy and systems that are resilient and sustainable, by promoting the financing and procurement and installation of those systems, by having standards which make it feasible to collectively then generate a market for both willful financing and rate of return earning and development of sustainable economies in these areas. So that's our vision, that with modern technology and standardization, that we can develop a sustainable ecosystem and move this transformation to a more developed world as quickly as possible. Again, we call this project in the IEEE the P2030.10. It is a standard that is very kind of hyper-focused on DC microgrids for rural and remote electricity, and I'll explain A, why microgrids, and B, why DC. But basically, this is a focused effort for what we might call off-grid initial embodiments of electricity systems for consumers. The type of standard that we're trying to develop is one that's somewhat anticipatory, but definitely enabling, in that it will enable people now to make products and to develop an ecosystem around this notion of remote microgrids that is sustainable. So we focus on things like compatibility and interoperability, so that those are essential elements of sustainability, because it gives us this kind of ability to have multiple sources of products and systems and so on, and to have systems that even if one entity falls out of the supplier stream, that others can replace it and so on. So we do focus on compatibility and interoperability. So you see in the context of this committee, it focus on power parameters and critical characteristics, and also interconnection compatibility, physical and electrical. Because by its very nature, we're talking about a system-level standard, which incorporates everything from sourcing of power to the actual interconnection to the various loads and uses of power downstream. So that's our goal, is to create this, to technically enable this kind of a electricity system that is safe and economic and can be used and deployed in developing and developed areas where central power transmission is and distribution is not available. And I won't go into all the humanitarian aspects of that, but you can imagine, just imagine your world without electricity, and you can imagine the enormous impact that bringing electricity on a sustainable and defendable way is going to change that part of the world. We see this as kind of a bottoms-up effort. It's not one that can be easily financed and directed from the top down, as it was in the United States in the middle 1900s, based on big government programs and, frankly, big spending. That's not possible here. So the way that we're approaching it is sort of bottoms up and based on renewable energy that will be transacted real time through these networks that are essentially fairly flat and more mesh-like in topology. So, and I'll go into that in a second. The technologies that we can depend upon today that are different than 100 years ago include much bigger use of solar and other renewable sources. Although we're not 100% going to depend on solar, we're going to allow for other renewables, and including electric AC power and such from combustion generators, if that's the only way to get it available. But we'll have systems, our standardization of multiple sources that can be combined at the sourcing side of the equation. But because a lot of those sources are going to be intermittent or not predictable, we will definitely take advantage of the growing availability of electric storage technology in coupling the sources and loads together with a buffer, if you will, of electricity storage. We'll depend somewhat, not extensively, because we want the system to be simple, but we'll depend on some solid state or digital, if you will, technology for the articulation of power, something that's increasingly available through the invention of things like isolated gate bipolar transistor technology and other technology can handle a lot more current and higher power levels. We will definitely look for a forward kind of view of this in terms of the increasing use of electrical loads. We know those initial loads will be relatively small, in many cases under 100 watts, for example. And that combined, or all the loads, not just a single load, but growing to multiple hundreds or into the kilowatts and so on over time. We have a strong desire initially, or we will have in this group, a desire to simplify and keep the systems very simple, both for service and operational means, but also to lower the total cost of ownership, which embraces everything from the initial capital investments all the way through the repair and maintenance and replacement costs. So inherently, though, because we're going to be dealing into a population that doesn't have an experience or familiarity with electricity in general, we'll try to, in the beginning at least, stick with very low voltages and limited currents to make things inherently safe wherever possible. So those are some of the key drivers in the technology. And when we look at that, we say, can you do all that and keep it that simple? And that's why we're really turning to DC as a first step, at least, and on a way to maybe hybrid embodiments as we progress. But in the beginning, perhaps a largely pure DC microgrids. What DC gives us as an advantage is that we eliminate the need to manage frequency, which includes phase control and phase-like balancing in the case of higher power levels. But this greatly simplifies the source combining that I talked about, where we might not be able to depend on a simple or single central source of power, where it's going to be distributed and reconfigured and so on and so forth on the fly, if you will, a self-healing network of power on the source side. So eliminating the need to deal with frequency and phase control and phase-like balancing and things like that is going to simplify that effort and make it much easier to do initially. The other part is that most of the practical electricity storage technologies are based on direct current storage. So this, too, by staying on the DC side from beginning to end, will simplify the task of incorporating this buffering capability of electricity storage without adding a whole bunch of conversions and management of that storage capability. Also, what that will give us at the load side is a DC output which can be articulated much more easily in terms of distributing the electricity, especially at this inherently safe level that we expect to see at the utilization ends of the grids that are being contemplated. So all of this put together by keeping it simple gives us a lot of things. One of the ones that, in addition to safety, which would be our first priority, but in addition to that, our almost next priority is the economics and keeping things lower cost. And by reducing the dependency upon sophisticated electronics and controls and such, we think we can reduce the cost of the end-to-end system and improve its efficiency to reduce the capital investment required up front. So that's why we're kind of focused on using DC initially. We're also contemplating that since we don't have a central source of power, that we're going to use a collective mentality for balancing the sometimes polychronic nature of the use, which means different people using different amounts at different times. So by putting it in a mesh, it gives that collective capability of sort of balancing the supply with the demand in that mesh. And we really look at it pretty similar to the way that the Internet operates, in that we want to do with electricity what the Internet does for information in this regard. Makes it pretty available throughout the 24/7 time frame. In any case, we kind of have focused a little bit in the contemplation of this vision on looking at how the Internet did this and why people have cell phones and Internet and they don't have power. And realize that it's really that having equal access at the point of access, a point of entry into the electricity infrastructure. So this is kind of an upside-down structure for distributed use dependency. It is bottom-up, so it'll be public because we want to, in a sense, be collective. So it isn't going to be enterprise-driven. It'll be publicly, structurally driven. We want to keep it simple, so we're going to try to make things so that there's a sort of a weak transactive cooperation between the individual elements of the system, so you don't have to depend upon a heavy bureaucratic administration of a hierarchical control scheme. And last but not least, because different dwellings and so on will be on and off the grid or the network from time to time, we really want it to be self-organizing so it can expand and contract as necessary. And when somebody drops out of the mesh, that it be self-healing. And all of that adds up to being resilient. And that's very important in a lot of the areas of the world that these grids will be hopefully used, need to be as resilient ultimately as those in the developed world are now. In order to sort of embrace and understand the scope of the work and to define it in a proper way, we're going to rely on some of the work that's already been done in many great organizations, including at the World Bank group, where they've defined sort of the scope of electricity access and broken that down into levels of tiers, what they call tiers of either service or availability. And we're going to use those definitions to help us work on this not as one big, project that's going to take, 10 years to figure out, but rather take it in chunks by tier or groups of tiers so that we can start small, but definitely keep in mind that there are more and more tiers as we go up with more and more requirements and dependency, all the way up to, I'm only showing 5 tiers here, but all the way up to tier 10, which includes the kind of service capability and access we have in the developed world. We're going to ignore a little bit, although we'll definitely use some of the brain power from those who have ventured into tier 0, which for the most part have been using combustion or fire, either candles or kerosene and so on, to provide things like lighting and cooking heat and so on and so forth. And ignore some of the very early work that were portable lanterns and things like that. Not that we're disrespectful of any of that, but it doesn't necessarily easily fit into the context of a more permanent and sustainable solution for permanent structures or semi-permanent structures like dwellings and later on commercial buildings and so on. So we're going to start with the presumption that this is a semi-stationary or permanent installation starting at Tier 1 access, which starts literally at about 4 hours of power, perhaps distributed throughout the day, but a total of 4 hours at the first level, but going up to 24 hours over time. So that will kind of give us a runway of activity and a sort of a priority of how we address this, starting small, but always keeping the eye on the next tier, the next tier, the next tier as we go through it. The multi-tier framework is very well defined and addressed in the documents of the World Bank Group, and if you're interested, I would suggest you, as a sort of a primer on this subject, go to the World Bank site and look up the multi-tier framework. They do cover things like water in the same way, water systems and so on. The ones that apply to electricity are designated there, and you can see how that's broken out. But it will cover things, everything from capacity to what duration of power, the reliability, quality, affordability, legality, safety, and health. So all the elements of the system, not just the technical operation or technical configuration of the system. So to give you an example of where the starting point looks to be, and this may actually be somewhere not at Tier 1, but maybe by Tier 3, where you have at least one or more sources of power. Typically, it's going to be solar. And by the way, I put some pictures in these slides just to show you that this work is starting to progress in some of these areas. In some areas, as many as hundreds of thousands of these isolated little power systems exist, but largely, almost entirely, from what we can tell, without standardization, which means that they're going to be very hard to sustain and certainly won't be interconnectable and interoperable over time. So we're trying to get in front of that curve as quickly as possible, but those systems already include things like battery storage and LED lighting and so on, and some even water pumping or filtration and things like that, which are all essential elements. And if you look real hard at this picture, you'll even see a cell phone in there because, for the most part, many, if not most of these dwellings or people that inhabit these dwellings do have cell phones. Sometimes they walk miles to charge them, which those of us in the developed world don't have to do unless you're at O'Hare Airport at 5 o'clock on a Friday and your cell phone has run out of power. You might be walking miles, too, to find an outlet. But seriously, these folks who have cell phones do sometimes walk many miles to just charge them so that they can maintain their communication ability. But in the progression that we see, combining those, and this is what differs from, say, 100 years ago in the United States when residential or remote microgrids were put together, they never got interconnected. Our view is that these independent microgrids will get interconnected, or some people will call them nanogrids at this level, will get interconnected into microgrids. Again, no central source, but shared distributed sources in the next level. And then eventually combining that with some shared regional sources or community sources like battery banks or solar farms or whatever to start to handle some of the collective bigger loads like agricultural, water pumps, and other semi-industrial kinds of power levels, which may not be available even in the collective resource of the mesh network of residential homes. But by adding those into the same grid, we pick up a lot of advantage in that. So again, starting to move towards what many of us call grids. But certainly up in the, connecting distribution between villages together in what we'll call district grids. Again, sharing power and sharing some of the distributed, even aggregated power structures of solar farms and things, right up to starting to connect into public utilities and other private utilities that will provide increasing resource into those grids at the community level in the form of regional grids, and eventually, and we won't get into the discussion of it, but eventually into national grids and maybe even continental grids, and hopefully someday maybe a world grid of electric energy. In any case, the focus of 2030.10 is really on the first steps of this progression. It's about the individual dwelling, the connection of very closely located dwellings together to start sharing resources collectively, and then the integration of some collective resources that are operated separate from the ones that are embodied or embedded into the individual dwelling. And that will be the first scoping stages of this activity as we move. This working group, by the way, is under the auspices of the Transmission and Distribution Group, the Power T&D Group, in the Power and Energy Society. So to put it in the context of everything else that's happening in the IEEE, that gives you sort of a perspective that this is again, it's sort of a hyper-focused part of the whole. It's not independent. And we'll be relying on all the other activities that are taking place in the IEEE at all these other levels, both in remote microgrids, for example, that are used to power cell towers and things in the more commercial and developed world, have a lot of capability offering into the inside of how to do this in this context or in this use case. In any case, Wayne Gutchow, who I believe is online, and maybe we'll say a few words at the end here, is the chairman, and I'm supporting Wayne as the eMERGE Alliance is trying to work closely with the IEEE and support this effort. It is an active project already. We're kind of in the organizing stage, so we've had several meetings, mostly focused on further defining the scope of the activity and a sort of road mapping of how we approach this. And from that, we've decided on what at least initial subgroups we need. And those subgroups are now, in most cases, I think, have leaders, and we're starting, the subgroups are starting to meet. The full working group will have monthly meetings. We expect that the vast majority of those meetings will be virtual, so that it shouldn't be, because of the global nature of this activity, we hope to engage people from around the world on a regular basis every month, and not just rely on face-to-face meetings, although we hope to have a few of those from time to time so everybody can get to know each other better. Again, we're just at the organizing stage, but very interested in having people join the effort to really resource the ranks of this effort, because we want to move at as quick a velocity as we can, and at the same time be as thorough as we always are and expect to be within the purpose of the IEEE. So with respect to that, if you are interested in this area, please let us know as quickly as possible so you can join the effort, particularly at this task group level, which is really going to set the stage for the ultimate development of the architecture and the standards. So what we've done is initially we do have identified 5 task groups. One of those task groups is going to focus on use cases. Another one is going to focus on identifying who are the stakeholders and how are we going to communicate with them, because we do need their help in defining not only the use case, but in defining the deliverables and making sure the standard is consistent with the expected deliverables, although we don't expect that a standard is going to be 100% of what's required, but it needs to fit in the context of all those other things. We're looking at market development because we want to learn what's out there, and to the greatest extent possible, take advantage of any intersection we can contemplate with what exists already. So we're looking at what's in the market, how it's developing, and what the likely path forward is once the standard is established. And we're also looking at all the existing standards. There are national standards. There are, of course, the background of all the safety standards that are available. So this standard, in many cases, will be subordinate to what we'll call the higher domain standards of safety, for example. But we want to make sure we're aware of all those standards and how they will be embedded in and referred to in this standard. So we expect a communication with all the existing standards groups and committees and so on who already have standards that touch into this or are working on similar standards for a different use case. So that's how we see the task groups being organized. So what we expect that would result from this standardization effort is that we would develop in this unserved portion of the world in electricity access a uniform and transparent market whereby the standard, the technical standards can underwrite the quality and performance standards for certification, provide some competition to improve choice and drive cost and pricing, to build the trust and confidence in installing systems and products, and a willingness on the part of the financing people to understand what their credit risk is and a willingness to underwrite that and to have buyers who have therefore the capability of investing in this infrastructure and effort, especially the service and replacement market, is one that continues to develop and be available over time. Specifically for the industry, those who see this as a market opportunity, we see creating the standard as quickly as possible to produce a faster time to market, such that early information on product requirements are clearly visible to OEMs and service providers, and how this all goes together and how their products and innovations might fit into the scheme. To give a better insight into the market, how big it is, who are the customers, what the competition is, and so on and so forth. To simplify the development of that and reduce costs and maximize efficiencies in development, product development, and service system development and the whole ecosystem. And to give leadership opportunities to companies who maybe haven't been looking at this market before, but have technology that can really provide something unique or an organizational uniqueness that will provide an opportunity and develop relationships with other companies who will be in this market space to provide integrated services and integrated product opportunities. In all, to provide business development opportunities for everything from startups to multinationals who have established business domains that they want to enhance. So in general, really what we expect to do with the standard is to facilitate the creation of this infrastructure, which will have both its humanitarian, social, and environmental and economic impact. We want to grow this market as fast as possible to bring down costs and to increase competition. But in doing so, we want to increase and not decrease the interoperability, which will be an important component of sustainability of systems like this in more remote parts of the world or less developed parts of the world. We absolutely want to encourage innovation, so we're going to err on the side of being minimalistic in the way we approach these standards. We're not going to overprescribe, hopefully, in the standards so that we can open up new market opportunities and new technical innovation opportunities. And we really, by keeping this on a global scale of effort, we want to prevent the duplication of effort, which I suspect is probably happening to a very large degree right now around the world in this particular market domain. So if you're interested in joining this effort, we would like you to contact Mike Kipnis, who is our IEEE Administrative Coordinator. Fantastic guy who helped us immensely. But if you contact Mike through his email and just let him know that you're interested in joining the effort at the IEEE 2030.10, and if you have a chance to review the slides and look at those task groups that I talked about, the 5 task groups, you might even want to identify which of those task groups you might want to provide your resource to. And so that's the primary way to get involved. If you do have additional information about what we're doing on the eMERGE Alliance side and how we work with IEEE and other organizations to do this kind of stuff, and we'll be demonstrating probably much of what happens in the IEEE 2030.10 in our trade show activities that we get involved in, like Solar Power International and the Green Build International and the Consumer Electronics Show, which is now more of a consumer technology show, both here in the United States and around the world. Please contact our Program Manager Beth Murphy, and she'll let you know how to get involved in eMERGE if you want to also join that side of the equation. But that's kind of all what I wanted to introduce today. As I said, we're in the organizing stage. So I'd like to sort of turn the mic, or at least the questions, over to Angelique, and maybe you can let us know if people have some questions about what we're doing, and we'll be happy to answer those. And I don't know if Wayne is going to be able to get on, but again, Wayne, thank you for joining as chairman, and maybe if you do have a mic, you can help me answer some of the questions.
Hi, Brian. Can you hear me?
Yes, I can.
Oh, great. Yeah, you did a terrific job of bracketing that. Thank you very much. Yeah, I'd just like to say, I've personally been involved with the IEEE since 2010, helping to design some off-grid power systems. And much like our task group leaders, I too have been thwarted by the lack of standardization. You start out with a goal by looking at a load, let's say in a village, and you try to decide what the duty cycle is, and what the power requirements and peak power are, and then you're basically limited to going on the internet and looking to see what manufacturers are offering. And it's really a backwards way of doing that. So I'm really excited to be helping out and participating in this new standard, because it's going to help. It's going to help me, and it's going to help everybody else that's involved in the design stage. So it's a very exciting time.
At this time, if you would like to ask a question, please locate the question and answer panel in the bottom right-hand corner of your screen. Type in your question, select all panelists, and click send to get your question in the queue. The Q&A will be moderated by Angie Rasky-Parashis. Please hold while we poll for questions.
And I just wanted to mention that Wayne is one of the true pioneers. Wayne mentioned that he started in this effort in 2010. But Wayne and others, and including myself, really started in this whole domain of renewable energy and integration of the renewables into the mainstream power systems back in the turn of the century here in 2000, around 2000, or even maybe a little bit before that. So there's quite a bit of history, and like I say, it's one of the areas that has remained sort of lagging in this area. There's lots of activities in the IEEE and eMERGE and other organizations around this whole notion of microgrids and DC power and renewable energy and so on and so forth. But this one clearly will focus on this area of energy access, and hopefully that will make a big difference in the world. So do we have any questions that you would like to ask, or are you still compiling those?
Yes, we have plenty of questions. Thank you very much for that presentation. So the first question is, the problem of non-access to electricity is also crucial in Africa, particularly in West Africa. However, we mostly rely on hydro and not fossil fuel. We do not have microgrids. What do you think are the best means of integrating remote DC microgrids in Africa?
Well, that's certainly one of the areas that we will explore. I know I am attending a conference that will be in Nairobi, Kenya, which I think is an area that might be a typical example of the area that this person is describing. But yeah, there is some power infrastructure there, like hydro. But what we have to do is figure out how do we develop this, in the sustainable way at the individual dwelling that he doesn't even have access to the hydro and all that, but over time connect it into the other available resources. So a lot of this is going to depend upon giving the confidence of the investment community to know that what they invest in is not only technically capable, but also safe to operate and maintainable over time. So one of the early parts of this equation is a standardization that allows the finance community, whether it's the World Bank, Asia Development, Africa Development Banks, USAID, IMF, and so on, to have the understanding of what it takes to have a reliable, sustainable system in technical terms. And that will greatly improve the underwriting capability of the finance community to issue loans, whether it's on a national basis or on a regional or even an individual basis. It's all the same. These resources, monetary resources to provide initial investment to kick this ball off, if you will, that will then provide an ability in these communities with these people to create their own economy over time in a sustainable way so that they can create for themselves wealth, which will lead to their own well-being and ability to sustain an effort in the social and economic world. So we see the first step, again, is helping to standardize that, to minimize risk of investment, and then to find the channels for that investment into the various regions of the world, including West Africa and many parts of Central Asia and South America and Central America that really are in desperate need of this help to get going. I hope that answers the question.
Great, thank you. What is the role of interoperability in remote generation?
So the role of interoperability is to provide a sustainable ecosystem, largely. So that means that instead of having one system that might be completely proprietary from start to finish, and I even referenced back in the United States that Delco Light system, it was called Delco Light, that by setting standards in that system, other players in the market were able to participate to provide competitiveness, which then leads to aggressive development of products and cost reduction and things like that under the purpose of competition, but also to provide it that when one company decides to get out of a market segment or to maybe move out of a particular region or not be able to serve it, that there are alternatives that are equally interoperable in the same system. And then last but not least, by making it interoperable at the basic level, that same interoperability theme will progress through the tiers or layers, if you will, of the microgrids right up to the point in time that it gets connected eventually, hopefully with a strong economic generating capability, if you will, from these grids to get to generate regional and national grids as well. So that interoperability is an essential thing, we think, in this whole effort.
Great, thank you. Why is the standard named 2030?
I don't know. It's a numbering system that's used by the IEEE. I'm not really sure exactly. I think it's a sequence number, but I could be mistaken. I don't think it's a date, if that's what's being suggested.
Okay, thank you.
We think by 2030 we would expect regions that will have the opportunity to deploy these types of grids and all that will be well along. We're not going to take that long to write a standard, I can assure you.
Thank you. How do you compare hybrid microgrids using solar, wind, and mini hydro to simple DC microgrids?
The notion of hybridity, I guess would be the word, if there is such a word, is that there are lots of things out there today in many parts of the world, in fact the majority, which operate in the AC mode of electricity. And we don't want to ignore the opportunity to combine the ability to, where appropriate, connect into and or use AC as well as DC power forms. It's not an essential at the beginning step, but it's something that you definitely want to keep your eye on. Where if you're going to start to employ either on the source side or the use side AC power technology, you want to understand and accommodate that in the way you structure the DC side. So again, it's not an essential in the beginning, but it's something that you definitely want to keep your eye on for the future integration, because that opens up a whole other opportunity to use the best of the best, if you will, of both AC and DC technologies.
Great. Next question. How many different power sources can one use in designing a nanogrid?
I don't know that there is a theoretical limit, because without having frequency, essentially the way the combination of sourcing is done is by voltage. Now, voltage then essentially is always going to default to whatever the highest voltage is that can deliver without sagging. So, but as long as you can put, and we put as many as 10 sources already, and more, and even more than that battery stacks on a bus, if you will, a collector bus, and not had any issues. So what will happen is that one source is slightly higher voltage, or producing a slightly higher voltage, the load will pull that voltage first until it starts to sag to whatever the next support level or the next source is, et cetera, et cetera. For example, the way that early microgrid worked back in 1916, the Delta Light microgrid, is that the batteries were essentially, the battery stack that they had was a 32-volt stack. All right, and you saw they were lead-acid batteries in glass jars and all that, and you used to put them on a shelf on the side of the barn wall, not inside the residence, but out in the barn. But the generator was set so when the batteries could not hold the voltage based on the current draw that the loads were pulling, the voltage would sag enough that it would turn on, and this was the Kettering invention, it would turn on the generator. So it would trip a relay, basically, that hit an electric starter motor that then started the generator set. The generator set was producing slightly over 32 volts, so it would act like a charge controller to the batteries. The generator was not directly connected to the loads. It was connected through the battery stack. So the battery stack became, if you will, the sort of leveling agent or the collector bus that held the voltage. So if the battery couldn't hold it, the generator came on and produced a slightly higher voltage and then protected the loads from voltage sag. So could you have 5 generators? Yeah, as long as they're DC, again, you don't have to do synchronization. Essentially, the way to look at it is DC is a non-synchronous technology in power, and AC is a synchronous one. If you use AC, you do have to synchronize your sources. And obviously, as you get more and more sources, it can become more and more difficult to do that. So the advantage, at least at this level of DC, is without having to synchronize, you can pretty much put as many sources as you want on the system. When I talk about that village microgrid, or even putting 3 dwellings together, essentially you're still on a common bus. The battery in one dwelling, the second dwelling, and the third dwelling, unless you provide some other means of shut-off and so on, and you might put some diodes in there for protection and things like that so you don't get backflow where you don't want it. But essentially, the system, whoever's using power, is going to draw on the whole system, all right? And then you have to figure out if you want to meter that. If you're going to do that on a revenue basis, you stick some meters in there to see where the power is coming from so you can reimburse whoever's supplying the power at any given time. But other than that, the basic technical side of it is you're really just talking about voltage. I hope that makes some sense to folks, that you can put as many sources as you want, and it doesn't really matter whether it's solar or hydro generation or whatever, as long as it outputs the voltage and you can regulate that voltage to put it onto the bus, then the source can be combined. We would expect even a bicycle with a generator on it, or any other kind of small device, or maybe a piezoelectric device that flaps in the wind, or any of that, and there's plenty of room for innovation here, can be connected into the system. The only requirement is to boost or buck the voltage to get it onto the collector bus, to within the collector bus range.
Great. Thank you very much. Next question. Can you please explain how this technology will allow a DC microgrid to interconnect with other DC sources where the DC sources of the past could not interconnect?
Yeah, there's a couple of reasons. One, in the what everybody calls the battle of the currents, right back in the turn of the last century, not this most recent, was the fact that you couldn't regulate voltages. You couldn't change voltages. So in AC technology, you had the advantage from the beginning almost, as it got perfected by Tesla and others, the use of a coil-wound transformer. And by being able to, one of the problems of connecting things together is not so much just connecting together, but how far does the power have to flow in a conductor before it gets to the load. And if that distance is too far, and I squared R would tell you that you got to get the voltage up to reduce the current so you don't lose everything in resistance heat in the wire. So in the AC world, you do that with a basic transformer, and you can do coil windings and step the voltage up and then bring it back down at the point of use, because the device is not going to be able to take the higher voltages typically. In the DC world, that technology didn't become available until the transistor was invented, and even more so, you could do that at very, very low power levels, voltages and currents, because that's what you do in semiconductors. But it wasn't available to the high power world, the power electronics world, probably until the 70s. The transistor was invented in 46, and the IGBT technology and other technologies that could make those voltage conversions and regulations weren't invented until the late 60s and 70s, and have ever since been perfected. So today we're using solid-state technology to step voltages up and down and to regulate them in buck-boost converters and big power systems. The latest power conversion, voltage conversion technology, IGBT technology, is now capable of converting voltages up in the hundreds of thousands of kilovolts. And so we've come a long way in solid-state technology, and principally on the back of isolated gate bipolar transistor technology as applied to some of even the newer substrates in the semiconductor world. So that's the big difference. You connect things together, you have to worry about distance, you worry about I squared R, and modern semiconductor technology has once and for all solved the problem of doing that in the DC world.
Great, thank you. Will this effort include any sociologists to understand what changes the electrification will do to local cultures? And does the program also include educating the people in the rural areas and making them aware of their responsibilities for being the end users?
The answer is, in an indirect way, yes. In a direct way, well, let me take them individually. On the sociology side, and what we would call not only the understanding of needs and development of use cases, because a lot of us, myself included, when I first thought about what people are going to use power for in for example, West Africa, I was probably pretty far off the mark. So by educating myself in trying to understand what people really needed in those different environments, you see that it's different maybe than what you thought it was based on your own experience and what your own environment is. So for sure, when you go back to those 5 task groups that we have, the one is called stakeholder identification and communication. That link is the one that we're going to rely on to bring that amount of information in. For example, both in terms of financing, but also in terms of the sociology, the political side, and so on, we need to take into account, although not directly in a standard are we going to address those things, but we need to take into account those things as it relates to how useful the standard will be or how useful a system based on a standard will be in the context of those other influences, whether they be economic, political, or social. So definitely the group will take those things into account to the best of its ability by getting volunteers and getting communication established with stakeholders in those component areas of the project. As far as servicing and setting up, methodology for that, I suspect that the standard will address that in the way that it looks at things like interoperability and all that, but not directly. In other words, in the standard, it's not going to force people to have a particular business model or service model for the way something gets deployed, but it's going to be a very strong component of consideration in the technical design to make sure that things are serviceable and, for example, partitioned in a way that elements of the system can be replaced or serviced without interruption to other elements. One of the nice things about the mesh network concept is that, for example, if one person's dwelling, which is now in this power stream, has an issue, or for whatever reason is pulled off the quote-unquote microgrid, that the rest of the grid still operates. That an individual, we don't want to make what we all call in the developed world the Christmas light effect, which is when one bulb goes out, they all go out. We want it such that if one light bulb goes out, all the other ones stay on. So that's the notion of doing the mesh network, which again is a lot simpler to do with DC because we're only having to worry about regulating voltage, and we can reconfigure the system with semiconductor switching and things like that, or simple droop control.
Great, thank you. And last question. As far as standard DC voltages are concerned, are we likely to see specific voltages for different applications?
Yes. In the domain at the very first entry-level tiers, we already know principally that, at least in terms of utilization voltages, that it's going to start around 5 volts, right, for charging cell phones and things like that. But it will probably range between 5 volts and 48 volts. So the service provision for power in that domain, which is all in what can be developed as inherently safe range of voltages, provided you also address current and a little bit of arc flash control and things like that, sparks and stuff, that you can easily address that in that range between 5 and 48 volts. Now, part of the challenge of the standards effort will be how do you address what we think are plateaus in that range, which are at 5 volts, 12 volts, 24 volts, and 48 volts. Now, those plateaus that exist in the marketplace today are essentially based on the design of batteries that typically were used in these extremely low voltage ranges, right? So you already had 12-volt car batteries, so it was logical that a lot of other things that were transportable and not on grid that would operate at 12 volts. So a lot of them started operating. If you put 2 of those batteries together, you get 24 volts. You put 4 of them together, or you have a communication system that may have been based on the original telephony design of 48 volts. So 48 volts got involved. So the standards group is going to have to figure out how do you address those utilization voltages in the distribution and collection system. It doesn't mean that the distribution will be at all those voltages. You certainly don't want to go very far with 5 volts with any kind of current. But it's not entirely out of the question that you might have subsystems, just like what we call device area networks today in computing. Enough to go in a single dwelling. You might be really okay with just 5 and 12 volts. But once you start going between dwellings, you probably are talking 24, 48 volts already, depending on how far you go. Now, ultimately, we're not going to limit it to that because, as I said, as you expand out to the community and so on, you got to think about the next distance that you have to go and what that voltage is likely to be. Now, in the developed world, there's a consensus building around the next voltage level being somewhere between 190 and 300 and 400 volts, somewhere around, I'll round that off to say 200 to 400 volts. Once you go to those voltages, you're out of the area that you can rely on intrinsic safety attributes of the power. So you have to bring in circuit protection, human protection, and a whole bunch of other safety features, which then naturally to get the safety, you have to raise the cost of the system. So we're going to try to stay in those lower domains that are more inherently safe and therefore require less economic investment and protection. But ultimately, we're going to have to move into the higher domains as the scope of the project widens over time.
Our thanks to Brian T. Patterson, and thank you again for joining us today.